Hi, so in this video I'm going to explain how Tarjan algorithm works and I'm going to also to make an informal proof at the end of the video of to explain why it works. So Tarjan is an algorithm to find useful to find strongly connected components. So of course you need to use it in a directed graph. So to explain to you how Tarjan works, I'm going to first do to show you how it works with a simplified version, which does not check every condition checked in the full version. And this simplified version, of course, does not work. It's just here to show you basically the flow of the algorithm, how it updates certain important values in the algorithm, the real algorithm. What is important, it's important to remember in Tarjan is that you will basically need a free data structure. So one will be an array of IDs. Another will be an array of low-link values. Actually, rather than being an array, sorry, I think it would be better to just take it as a dictionary. So a Python dictionary or a Java hashmap, you know. So yeah, so we will have two dictionaries, two hashmap, and as well as a stack. So we will have a stack. So with these three basic, actually you also need you need the four, but this is you need a fourth data structure, which is on stack, to check if some elements are in the stack in constant time, but this is only for optimization. It's not necessary to have it to make the algorithm work, but so you could also have a dictionary. So with those four data structure, you can make Tarjan work. You only need to remember basically you need IDs, low-link values, and stack. So in the simplified version, I'm going to explain how you use the IDs and the low-link values. So the simplified version is just going to show you how we update those things. It's not going to use the stack or unstack, and it's not going to show you how to get the strongly connected component, but the full version is going to make use of the stack as well as the IDs and low-link values, and it's going to show you how we get the strongly connected component from the stack. So to show you the simplified run, we are first going to take a graph. So let's take this graph. So as you can see, we have two strongly connected components in this graph. So here and here we have another one. So how does the simplified Tarjan work? So basically, Tarjan is, at its heart, it's a DFS with some other data structure, you know, and a stack. But at its heart, it's a DFS. So what you do is actually you are going to visit a node, and each time you visit a node, you are going to assign to it an ID as well as a low-link value. So you're going to assign to it an ID and a low-link value. And when you assign to it an ID, the low-link value is the same as the ID. And and you ask, okay, if the ID is the same as, if the loading value is the same as the ID, what is the use of having loading values? So actually, you will see that loading value can be updated. The ID will always remain the same, but the loading value can be updated as we run through the graph. So, okay, A was visited, and and now we need to visit its neighbors. So we are going to visit the neighbor of A, which is E, and we are going to assign to it an ID and a loading value. So same here, ID1, loading value of 1. And we mark it as visited. Okay, and now we are at E and we need to visit the neighbor of E. So we see that A is the neighbor of E, but A has already been visited. So we don't visit it, but we can use its loading value to update the current loading value. So, okay, we say, and how do we use it? Actually, what we do is we take the minimum of the neighbor loading value, 0, and the current loading value, which is 1. So the minimum is going to be 0, so we update it. And here we update it. And now we backtrack. And as you backtrack, you can always use the backtracking loading value and min it with the current loading value. So here it will be 0, min of 0 and 0, so you will not update anything. Okay, so now we are at A, and we are going to explore the remaining neighbor of A, which is B. So, okay, we explore it, we arrive at B, we assign to it an ID and a loading value, okay, and now we need to add it to the dictionaries. So we are going to have B is 2 and B is 2, okay. And now we are going to continue exploring. So, okay, we arrive at C, like usual in the DFS. So we are going to have C here, C3, and C3 here. We continue exploring, 4 and 4. Okay. And of course, I didn't mark them, but those guys have all been visited now. And now we are at D, and we search for the neighbor of D, so we find B, but B has already been visited. So we don't visit it, but we can use its loading value to update the current loading value. So we do the min of 2 and 4, and we get 2. So we update it, and here we update the loading value of D to 2. And as we backtrack, we can always use the loading value of the backtracking node and to update the loading value of the node in the upper call. So we update it to 2. We do the minimum of 3 and 2, so we get 2, and we update it here. And we backtrack. Of course, the minimum of 2 and 2 is 2, so nothing. It doesn't change. And we continue backtracking. Minimum of 0 and 2, it remains 0. So now we have finished everything. And here it's basically incorrect, but this version shows you how to use IDs and loading value and how they are updated. But the truth is, in the real version of Tarjan, this is not really how things works. There are some conditions which we need to verify before doing the minimum of the loading values to update the loading value. And only if this condition is checked, you can update the loading value. Otherwise, it must remain the same. So I will explain what is this condition in the full run now. And I will also explain how we use the stack to find the strongly connected component. Maman, tu vas faire du bruit parce que je suis en train d'enregistrer une vidéo, donc ça tombe mal, hein. So in the full run of the algorithm, so now for this full run of the algorithm, we are going to make use of the stack, and I'm also going to show you the condition we need to check. So as usual, we are going to do a DFS on the graph, and we arrive here. Maman, je rigole pas. Putain, mais t'es sérieuse? Ne fais pas de bruit. Mais oui, mais bon. Je m'emmerde depuis tout à l'heure et t'arrives là comme ça. So now in this so now that we have cleared everything, we are going to run the full version, so the real Tarjan algorithm, which makes use of the stack, and we are also going to check the condition, the correct condition before updating the loading values. So we begin as usual with a DFS. So we arrive at A and we assign to it an ID and a loading value. So okay, 0, 0. And what is different from before is we are also going to put A on the stack. Okay, A is on the stack now. And we mark this node as visited. Okay. And we visit its neighbors. So, okay, we visit the neighbor of A, which is E. We assign to it an ID and the loading value. Okay. And we put it on the stack. We mark it as visited. So of course, I mean, you also need to mark, not only put it on the stack, but you need to mark the element that you put on the stack as on the stack, you know. So E is true and A is true and E is true. So they are on the stack. And now you continue exploring the neighbor of E. So you see that A is a neighbor of E, but A has already been visited. So you don't visit it, but you can perhaps use its loading value. But before being able to use the loading value, there is a condition which you must check. So what is this condition? The condition is that A, the neighbor loading value, which has already, the neighbor node which has already been processed, it must be on the stack. So in this case, A is on the stack. So we can use its loading value and min it with the loading value of E. So basically on stack, so the condition is on stack of neighbor. If it's true, then we can use a min. So we min it, and we update the current rolling value to 0. So basically we update it here. Okay. And now we can backtrack from E. But there is something we need to check. So this is not very important at this moment of the graph, but it will be important here. Is what is important is that before backtracking, you need to do a small check, which is the current ID equal to the current loading value? So is IDs of current equal to ID equal to loss of current? If it's the case, we will need to do something, but as of now, this condition does not hold, so we can just skip this part for the moment, and I will explain how it works here. So we can just backtrack safely since this condition was not checked. And we arrive here, and now we still have a neighbor node to explore from A, which is B. So we are going to explore B. We set its ID and loading value. Okay. Okay. And we put it on the stack, and we mark it as on the stack, and we mark this node as visited. And now we continue doing our DFS from B. So we update here, we update, we put it on the stack, we put it as on the stack, and we continue our DFS. Okay. So yeah, we put it on the stack, we mark it as on the stack, and of course, yeah, we mark everything as visited here. And now we are at D, and we explore D again with DFS, and we explore the neighbor of D. So we find that B is a neighbor, but it has already been visited. So we don't visit it, but perhaps we can use its loading value. So to do this, we check the condition, is B on the stack? B is on the stack, this is true. So we can use its loading value to update the current loading value. So we do a min of 2 and 4, and we get 2. As we backtrack, there is no such condition that we need to check. It's only in the backtracking case, we can always use the loading value of the backtracking node, and so we can update it by doing the min of the backtracking node with the min of the current node, and we get 2. So of course you will need to update those things here. And as I told you before, as you backtrack, there is this condition which you need to check, but as you see, before backtracking from the ID and the loading value is different, so we can safely backtrack. Same for C, since we updated the loading value before backtracking, the ID and the loading value is different, so we can backtrack safely. But as we arrive to B, we min the current loading value with the loading value of C, and it remains 2. And now you have explored the only neighbor of B, which is C, and you need to backtrack from B. But the condition holds, and you need to do some things now. And what is this something? Basically, you are going to use the stack to find the strongly connected component. And what you will do is basically you are going to pop element off the stack until the element that you pop is equal to the label of the current node. So basically you're going to have vol is equal to stack pop, And while vol is different from current, you are going to do vol is equal to stack pop. So you're going to pop element of the stack until until you have popped every element, including B. So we are going to pop this element. So we begin popping element, and what this does basically is that it finds the strongly connected component. So basically, when this condition when this condition holds, you open a new strongly connected component, and the element that you pop from the stack, you will put it in this strongly connected component. So at first we pop D from the stack. Okay, we pop D, and we put it in the strongly connected component. Okay, but then D is different from B, so we need to continue popping element. So we pop C. Okay, and we put C into the stack, into the strongly connected component. Okay, and then C is still different from B, so we continue, we pop again an element, and we put it in the stack. But now B is equal to B, so we stop this this function, this part of the algorithm, and we just backtrack safely. As we backtrack, we again do the minimum of the current loading value with the neighbor loading value, and it's equal to 0, so it doesn't change. But now every neighbor of A has been visited, and we need to backtrack from A. But before backtracking, we need to do this check. So is the ID of the current node different from its loading value? In this case, no. So we are going to need to do this procedure of popping off element from the stack. So it also tells us that we need to open a new strongly connected component. And we are going to pop element of the stack. So yeah, we pop E of the stack, and we put it here. And is it equal to A? No, so we need to pop A and put it in the stack. Is A equal to A? Yes, so now we can stop. And as you see, the strongly connected components were found correctly. So, of course, another question is, why does this procedure of using the stack works? Why does it work? Well, of course, what you may wonder now is, why does this procedure of using with the stack works? Why does it find correctly the strongly connected component? To understand why it works, you actually need to consider a graph and think of it as a set of strongly connected components. So basically, any graph is a set of strongly connected components. You don't know how many strongly connected components there are in your graph, but you know that there is at least one strongly connected component, yeah? So each of those big circle represents a strongly connected component with nodes inside. And there's something else that you know about those strongly connected components. And it's that there is at least one strongly connected component which is going to have no outgoing edges toward another strongly connected component. And this is true because if it wasn't the case, it would mean that we would have a cycle between strongly connected component, and basically it will mean that they actually form all of those guys, the strongly connected component in the cycle will actually form a single strongly connected component. So we have at least some strongly connected component with no outgoing edges. So consider a strongly connected component with no outgoing edges. So this one, SCCN, and where this one is SCC1 and this one SCC2. I don't really care. And now consider, as we do our DFS in Tarjan, consider U to be the first node of this strongly connected component that we meet. So it's the first node. There must be a first node of a given strongly component that we meet. And so this is the first node. What it means is so that every other node of the strongly connected component have not yet been visited, okay? They have not yet been visited. Also, I have made a mistake with the, it must form a cycle, so okay. So every other node of the strongly connected component have not yet been, or this strongly connected component have not yet been visited. And O is the stack at this point in time. The stack will basically be, we don't know what are the nodes we have visited before U, we don't know. But we know that every other node we are going to visit after U is actually going to belong to this strongly connected component. If we do a DFS from here, since there are no outgoing edges, and since so it means you are not going to visit node outside the strongly connected component, and since every other node inside the strongly connected component is reachable from you, every node here is going to be visited after this point in time. So we know that all the node here belongs to this SCCN. And here is the important thing with the IDs and the loading value is, so when we reach U, we assign to it a loading value and an ID of I and I, okay? And so we visit the neighbor of U, so we assign A plus 1 and A plus 1, A plus 1 and A plus 2 and A plus 2 as ID and loading, and A plus 3 and A plus 3. And basically, since this is a strongly connected component, we know that there will be some node that will reach, which is going to have an edge toward U. But what does this mean? It means that it will mean its loading value with the loading value of U, which is I, and this will backpropagate I as a loading value for every node of the strongly connected component. And this means that for every node of the strongly connected component, their ID will be different from their loading value. And we will be able to backtrack safely each time without touching the stack. So we know that when we reach again U, every node of the strongly connected component will be after U and will not have been touched. And this is why when you reach the node U, which correspond to I, the ID equal to the loading value, you can safely pop everything and you can know that you will have found a strongly connected component here. And basically, this is you can generalize it to the other strongly connected component, because so for example, let's take so we're going to take a perhaps a bigger stack to show you. But basically, say our DFS began here. So our DFS began in the SCC in SCC2. So what happens is you visit some nodes in SCC2, but then say you don't visit all the nodes in SCC2, but you visit now the node U of SCCN. So now what happens is, okay, we visited some node of SCC2, and then we visit all the node of SCCN. And as we backtrack here, and as we reach again U, we pop off every element of SCCN, and now we are still at this point in time. No, so now everything here is finished. And now perhaps we are still going to visit some other strongly connected component. Okay, so we are going to visit it before visiting all the nodes here. And okay, so what will happen is, because of what I explained for SCCN, we're going to explore all the nodes here before visiting any other strongly connected component. So as we explore these nodes and as we backtrack, we get again a new strongly connected component, and we then pop it from the stack. And so now there will be some point where all the strongly component, the outgoing edges, I mean, there will be some point where all the strongly connected component reachable from SCC2 will have been entirely visited. And that's it. At this point in time, SCC2 will only have to visit its own node. So it will visit its own node basically. And then once it has visited its own node, it will reach the point, say V, which is the first, which is going to be the first node of SCC2 that we met. And we will have the condition ID is equal to low-link value. And we will pop everything off from which corresponds to SCC2. And this is basically why it works. Thank you for watching. Bye.